S3, S4 Physics, potential dividers. Potential dividers. A potential voltage divider circuit is a very useful circuit. The circuit usually consists of a supply voltage and resistive components, usually two, connected in series. The supply potential or voltage is divided up across the resistors in the circuit. Here's an example of a potential divider. We can see on the circuit, this is our potential, our voltage supply. Here we have resistor R1 and resistor R2. There'll be a potential V1 across resistance R1 and a potential V2 across resistance R2. And thinking back to our basic circuit rules, we know that Vs is going to be equal to V1 plus V2. We can also think of this as a way to find V1 and V2. If we know what V1 is, we can say that V2 is equal to Vs minus V1, or V1 is equal to Vs minus V2. Now we can calculate the values of voltage 1 and voltage 2 by using Ohm's law. If we know the values of the resistors here, we can work out the total resistance, RT, is equal to R1 plus R2, and then the current in the circuit is going to be equal to the supply voltage divided by the total resistance. We can then use this current with values for R1 in order to find V1. V1 is equal to I multiplied by R1. V2 would be I multiplied by R2. But that's a lot of calculation. What we can use instead is a different formula which brings all these things together. For all potential divider circuits, the following is true. The larger resistance will always have the greater potential difference across it. If you think about it, the resistance is larger, so the current is going to take more time to go through it. The sum of the individual voltages, as said in the previous slide, will be equal to the supply voltage. V1 plus V2 equals Vs. The ratio of the potential differences of the voltages depends on the ratio of the resistance values. V1 over V2 is equal to R1 over R2. What this means in effect is that if R1 is bigger than R2, V1 will be bigger than V2. If R1 represents 1/3 of the total resistance, V1 will represent 1/3 of the total voltage. This equation is on the relationship sheet, and it can be very, very useful to us if we only have certain values. For example, if we don't have the supply voltage. We could also write this as V1 over V2 is equal to R1 over R2, which you may see in some examples. So here we have a potential divider circuit. We have supply voltage Vs. We want to find V1, and V2 is equal to 16 volts. In the previous circuit, R1 is equal to 20 ohms, R2 is equal to 80 ohms, and you're asked to calculate the value of V1. We use the ratio equation for this because we don't have a value for the supply voltage. V1 over V2 is equal to R1 over R2. V1 over 16 is equal to 20 over 80. V1 over 16 is equal to 0.25. V1 is equal to 0.25 multiplied by 16, giving us a value of V1 to be 4 volts. In the second example, we have a value for V1 as 25 volts and a value for V2 at 10 volts. In the previous circuit, R2 was equal to 80 ohms, and we're asked to calculate the value of R1. Again, we use the ratio relationship. V1 over V2 is equal to R1 over R2. 25 over 10 is equal to R1 over 80. And because we have this as fractions, we can cross multiply. So in cross multiplication, whatever we want goes on the left-hand side. In that case, it's VR1. And then whatever's opposite to R1 goes on the bottom line, and the other two, which are opposite to each other, goes onto the top line. So R1 is equal to 25 multiplied by 80 divided by 10, which is equal to 200 ohms. So we're going to be doing some practice calculations, and they're all based around this circuit, where I have a supply R1 and R2 with potentials V1 and V2 across them. For the previous circuit, you're asked to calculate the missing values in each row. I have V1, V2, R1, I need to find R2 here. So this set of questions will help test our ability to be able to use the equation V1 over V2 is equal to R1 over R2 in order to be able to calculate any of the missing variables. You can take a moment just now, pause the show, and see if you can do the calculations yourself. Answers will follow. Here are the answers to the questions. Make sure to check your own solutions, and if you didn't get the correct answer, try having a look back at the previous examples. Not all potential divider circuits can be solved using ratios. An alternative equation would be to use V2 is equal to R2 over R1 plus R2. Now this equation can be used instead of going through the Ohm's law calculations we showed earlier on. We have R1 plus R2 on the bottom line. That's the total resistance. So an alternative way to look at this would be V2 is equal to R2 over RT multiplied by Vs. Again, is about proportions. R2 over RT represents the ratio of the resistances. So we're finding out what part of the total resistance is taken up by R2. So if R2 takes up a quarter of the total resistance, then V2 will be 1/4 of the total voltage supply. So by working out R2 over RT, we're working out what portion of the total resistance is taken up by R2, and that will tell us what portion of the total voltage is cross V2. So here's our potential divider circuit again, Vs, R1, R2, and I'm wanting to find what the value of V2 is. So if I'm finding the value of V2, I'm going to be concerning myself with the value of resistor R2 and the total resistance of R1 plus R2. So the value of R1 in the previous circuit is 150 ohms, R2 is 300 ohms, and you're asked to calculate the value of V2. In order to find the solution to this, we really need to find the value of what's in the bracket first. So we are taking R2 as being the resistor we want to find the value of voltage across. R1 plus R2 is the total resistance. 300 over 150 plus 300 gives us 0.67. So 0.6 seconds represents the fraction of the total resistance R2 takes up, and that will be the same fraction of the total voltage we'll find across V2. So V2 is going to be equal to 0.67 times Vs, just as R2 is 0.67 times RT. We take our supply voltage as being 12 volts. V2 is going to be equal to 8 volts. Here we have a potential divider circuit again, and again we're trying to find V2. Remember our supply voltage from before is 12 volts. So for the previous circuit, find V2 for each of the rows. In this, we have to take into account we have a new value for the supply voltage, as written here. We have values of R1, we have values of R2, and for each example, we're trying to find the value of V2. But we're using the same equation each time. V2 is equal to R2 over R1 plus R2, brackets, multiplied by Vs. So when calculating V2, it's useful to find whatever's in the brackets first in order for us then to use that with the supply voltage. Remember, if you don't have a value for the voltage supply, you're probably going to be using the ratios equation instead. That is V1 over V2 is equal to R1 over R2. Here's the answers to the previous questions. Remember to check your solutions against the ones you tried yourself. If you get any incorrect, look back at the previous examples and have a go again. Here's a past paper question, and this one's slightly different. In the previous questions that you had, you were looking at working out ratios or working out using the potential divider equation to find values of R1, R2, V1, or V2. In this one, we're looking at your ability to understand what happens if we change those ratios. So in this circuit, we have a component called a transistor, which you may have come across before. The transistor is an electronic switch. So that electronic switch will only turn on when it reaches a certain voltage. For a transistor, it's actually 0.7 volts. So if the value of the voltage across R2 here is too small, the value across the transistor will be too small as well, because these two are in parallel with each other. So whatever the voltage across R2 is the same as the voltage across the transistor. If this voltage is 0 volts, this voltage is going to be 0 volts as well. We're told in the question the variable resistor is adjusted until the LED switches off. The temperature of the thermistor is now increased. This is our thermistor here. So remember, our thermistor is a temperature-dependent resistor. And for the temperature-dependent resistor, if the temperature goes up, the resistance goes down, and vice versa. We're told the temperature of the thermistor is now increased. The resistance of the thermistor decreases as the temperature increases, which is what we expect. Which row in the table describes the effect of this change on the voltage across the thermistor? That's this one here. The voltage across the variable resistor, that's one there. And whether the LED stays off or switches on. This is our LED, our light emitting diode. The light emitting diode will only produce light if current's flowing through the transistor to it. The transistor will only switch on if it has enough voltage. So let's see what's happening. So the temperature has now gone up. Temp has gone up. That means the resistance of the thermistor has gone down. Now, if the resistance of the thermistor has gone down, that means the resistance it represents is a smaller portion of the total resistance. Because remember in the equation, V2 is equal to R2 over R1 plus R2 brackets multiplied by Vs. As R2 gets smaller, this number in the brackets gets smaller as well. So the smaller the value of the resistance, the smaller the value of the voltage. So the resistance across our thermistor, remember our thermistor is this one here, has gone down. Because the resistance has gone down, the voltage across the thermistor must also go down. So that means we're looking at either A, B, or C. These can't be right. If this voltage goes down, remember our voltage rule for a series circuit, Vs is equal to V1 plus V2. So if this one, V1, that's the voltage across our thermistor, let's rewrite that. Vs is equal to V across the thermistor plus the voltage across the variable resistor. If the voltage across the thermistor has gone down, that means the voltage across the variable resistor must have gone up because they have to add up to the supply voltage, it's a constant value. So again, looking at our table, voltage across the thermistor decreases, voltage across the variable resistor increases. That's the only one that's correct. And because the voltage across the variable resistor goes up, that means the voltage across the transistor goes up and the LED switches on. So the answer must be A.